right, so over the past several days, you guys have been learning about the definition of the derivative. You've been learning how to take the derivative in terms of calculus. So now what we're going to do is talk about graphs and functions that you cannot take the derivative of. So there are graphs and there are functions in which a derivative will fail to exist. And what we're going to do today is explore where those graphs and functions are going to fail. So a function is differentiable at a point if you are able to differentiate, you are able to find a derivative, you are able to find the slope of the tangent line, or you are able to find the slope of the curve. These are all things that we can say are true if a function is differentiable. These are all statements we can say are true if a function is differentiable. If a function is not differentiable, then we say that it fails to have a derivative at the point A, which means that the slope of the secant line fails to approach x at A. So what that means is that we cannot find a limit, or that the limit does not exist. In terms of a graph, there are 4 easily identified instances where a derivative will fail to exist. A corner, like in an absolute value. A cusp, like in an exponential. A vertical tangent, and any points of discontinuity. So if a function is not continuous by our definition of continuity, then it will fail to have a derivative. If a function is discontinuous by our definition of continuity, it will fail to have a derivative. So oftentimes, AP will use wording like a function is twice differentiable. If a function is differentiable, then that implies continuity. However, continuity does not imply differentiability. Does that make sense? Differentiability implies continuity. Continuity does not imply differentiability. And a cusp, corner, and vertical tangents are examples of why continuity does not imply differentiability. Yes. We're going to see in about 2 slides. You're good. He's just thinking ahead. So example number 1, a corner. The easiest, most prominent example of a corner is an absolute value. If you think about an absolute value, what is the slope on the left side of that function? The slope over here of this curve is -1. What is the slope of the right side? So since the slope on the left and the slope on the right are different, then the left-hand limit wouldn't equal the right-hand limit as we approach 0. Therefore, the function is not differentiable at 0 because the slopes of the tangents are not the same. A cusp is like the little birdie looking graphs. So it's when you have an exponential to a fraction. So when you have a variable raised to a fraction, you're going to get a cusp. A cusp is approaching infinities from the left and from the right. Therefore, the infinities are going to be opposing because this is a decreasing slope on the left and an increasing slope on the right. So you'd have a negative infinity and a positive infinity. So again, the left-hand limit won't equal the right-hand limit of the derivatives. Therefore, not differentiable. Only at the cusp. Only at this point right here. It's not drawing. There we go. So the curve is differentiable here, there, etc. It is just not differentiable at the cusp, at the actual point. A vertical tangent is where you have a graph that is vertical at some point. So at x equals 0, this graph is vertically straight up and down. So this function is not differentiable at x equals 0.
How's that a function? How would that pass the vertical line as is a vertical line in the function?
Because by definition, in order to be a function, for every x, there is only one y. So there are no x doesn't, if you would plug in x values here, you're never going to get a duplicate answer. Like if I plug in 1, I'm always going to get 1.
So if you plug in 0, multitude of answers on that vertical line?
No. Like yeah, plug in 0. F of 0 is, yeah. And f of 0.000001 is a really, really, really small number close to 0, but not actually 0. Like every x value is unique. Does that make sense? So when it fails is to be like, so why it fails, like where it's vertically tangent in there, is because as you're approaching from this direction, it's so steep that it's going to infinity. And when you're approaching from this direction, it's so steep, we're saying it's negative infinity. So what's happening is when you approach it from one side versus the other, you're getting opposing infinities. Therefore, it's not differentiable. And again, we're talking about the derivative. We're not necessarily talking about the original. Example 4, f of x equals 1 for x values less than 0, and f of x equals negative 1 for x values greater than 0. So we have this graph that looks like that. So at x equals 0, what do we have occurring? Jump. Discontinuity, right? So let's talk about this. What is the limit as x approaches 0 from the left? The limit as x approaches 0 from the right? Let's talk about the derivative. What is the derivative of -1? What's the slope of that derivative? 0. So f prime of the derivative at -1 and 1 is always 0. But if you tried to find the derivative at 0, it does not exist. And we're going to talk a little bit more on how and why to find that. And we're going to talk about left-hand derivatives and right-hand derivatives in a little bit. Okay, so let's graph the next example. So this is an absolute value function shifted up 3 and to the right 2. So that means that the vertex is going to be at 2, 3. Therefore, the function is not going to be differentiable at that vertex, which will be at x equals 2. Let's rewrite the absolute value as a piecewise. So we have the absolute value of x minus 2 plus 3. So for the positive side, you get the absolute value becomes x plus 1. And you can see that if you extended your graph down. And then over here, it's like negative x. And then the y-intercept is 5. So in order to split the absolute value, you put a negative in front of the absolute value stuff, and you drop your absolute value for the positive side. And then the split is at 2. So this will be x values greater than 2. This is x values less than 2. And we know that at 2, it's equal to 3. So going into our new idea about derivatives and the definition of the derivative, let's use the alternate form to find the limit as x approaches 2 from the left. So this is what we call the left-hand derivative. Like we had a left-hand limit, we have a left-hand derivative. So the limit as x approaches 2 from the left, using the alternate form, will be f of x, which is x negative x plus 5 minus f of 2, which is 3, all over x minus 2. Okay? And then in the numerator, you will notice you can take out a -1, right? And that'll give you what's in the denominator. So if you factor out a -1, you get x minus 2 over x minus 2. Sorry, I didn't write my limits. And that equals -1. So the limit as x approaches 2 from the left is -1. That should make sense because the derivative of that is the slope of that, which is -1. And then what we want to do is find the right-hand derivative. So you're going to find the limit as x approaches 2 from the right, which would be x plus 1 minus 3 over x minus 2. So you get x minus 2 over x minus 2, which is 1. And you can see that the left-hand derivative does not equal the right-hand derivative, therefore not differentiable at x equals 2. Good? Okay, so that was like the algebraic reasoning. Okay, the function's derivative is equal to an infinity. So what happens if your function's derivative is equal to an infinity? What do you think we're going to do for this function? Or where is this not going to be differentiable? Do you want to see what it looks like on a graph? Go ahead and type it into your graphing calculators. What? No, just type in h of x into y equals. So hopefully when you type that into your graphing calculator, we see the curve. We see that the function sort of looks like this, and it goes whoop. So what you should notice is that this point in here is going to give you that vertical tangent. So where you have a vertical tangent, it's not differentiable. So where do you think that point is occurring? What value of x? 3. Because of this point or idea in here, right? So this is really kind of like saying x minus 3 to the 1/3 plus 2. So this is a cubic, sorry, it is our cube root shifted up 2 units, and cube roots will have vertical tangents at that point with which they are shifted. No. If you wanted to show it algebraically, this is what it would look like. The limit as x approaches 3 from the left, the limit as x approaches 3 from the right, and then what you would have is x minus 3 of 1/3 plus 2. And obviously, it's not on the original, it's on the derivative that you're going to get that negative infinity. So this is like your f of x minus f of 3, which in this case is 2, because 3 minus 3 is 0. So you get 2 all over x minus 3. And then your vertical tangent's going to occur in here, because you're going to end up getting a number over 0, which will give you, well, in this case, 0 over 0, but then when you do your complex conjugate, you get the number over 0, which will give you an infinity.
How do you turn this off?
Oh, math, go to math. And then, or sorry, mode, and then go down to full. And highlight full.
Thank you.
You're welcome. So from this side, it's going to positive infinity. And from this side, it's going to negative infinity. So the left-hand derivative doesn't equal the right-hand derivative, therefore the derivative does not exist. Oh, you want your table. What do you mean the negative?
So for the last lesson, whenever we were doing that
The
stuff,
limits, yeah.
we put that, but you turned that off.
Well, those are the x values it's plugging in. You would have to go to table and change it. Or you can go to second window and you can just change it to auto. But like, okay. You're welcome. Yes. There's no bells ringing. Right, so this is how I introduced this lesson. I introduced it by saying differentiability implies continuity, but continuity does not imply differentiability. This theorem is such an important statement in calculus. You need to know from here on out, if you are told something is differentiable, you know it's continuous. If something is differentiable, you know it's continuous. Because as we progress through the course, there will be times you will be told the function f of x is differentiable, but in order to continue and prove what you need to be able to prove, you need to be able to say then f of x is continuous. So by the theorem, if f has a derivative at x equals a, then f is continuous at x equals a. And I have continued to say that it is important to recognize the converse of this statement is not true, and that continuity does not imply differentiability. And an easy example of that is an absolute value function. An absolute value function is continuous, but not differentiable everywhere. So I think I corrected the page numbers, but then I sometimes forget to save my PowerPoints. So let me confirm that that is the correct page. and problem set. And what? All right. So nope, we have to change our pages. I knew it.